Okay, so I think we can start. Good morning or good evening, everyone, depending on where you're connecting from. I'm Chiara Falsetti. I'm an assistant professor at U Delft, and today I'm very happy to introduce Dr. Zhenying Wang, giving her a seminar today on wetting and evaporation from single to multi-component droplets. Dr. Zhenying Wang is an assistant professor at the Department of Aeronautics and Astronautics in Kyushu University, Japan. She obtained her PhD degree in 2019 from same university, and her research is mainly focused on fluid-based energy systems, micro-nanoscale phase change, and wetting of complex liquids. She's now, as I said, assistant professor, and she's holding 3 research grants, including the JSPS Kakenhi for Young Scientists, the Toyota Scholar Program, and the KAO Crescent Award. Today, we will hear her research on, as I said, wetting and evaporation, and she's very looking forward to discuss any academic problems or questions related to this, and also in relation to new visualization techniques and numerical methods with the attendees. So, given this short introduction, now I leave the word and the floor to Dr. Wang.
Okay. Thank you, Chair, for for being the chair of my talk. And so I'd like to thank the organization from the Professor Bucci, from Dr. Masu. Yeah, so today I'd like to talk about the wetting and evaporation from single to multi-component droplets. So I think it is actually a basic topic which have a lot of relevance. It is relevant to a lot of other topics such as boiling, condensation. So actually, so what I talk here is about the governing mechanisms. So that I hope that I can give you some idea on all the governing mechanisms in a easy to understand way. Okay. So actually, so when we talk about wetting, so actually we usually sorry, I need to get this off. That's okay. Yeah. So actually, when we talk about wetting, usually we will talk about static wetting or dynamic wetting. So for the state of wetting, especially in the static case, we usually will talk about the state of when a droplet meet a solid surface. So according related to the surface energy of the droplet and as well as the solid substrate. So actually we can divide it into total wetting or partial wetting, or hydrophobic partial wetting, or no wetting cases for super hydrophobic substrate. So actually, what we care about wetting is that actually we need to control the wetting condition for different application scenarios. For example, when we talk about evaporation-based thermal management, we usually would like a good wetting, because a good wetting would avoid dry out, especially in this evaporation end, or for example, in a heat pipe system. And also, what's differently when it comes to condensation, usually we do not want a good wetting, because a quick wetting transition would increase the thermal resistance, and it will worsen the condensation performance. So that is the importance of wetting, and this is the static wetting. So actually things become even more complex when we come to dynamic wetting. So different from a sensor droplet on a solid substrate. So actually, if we consider the dynamic wetting, when we put a droplet, when a droplet firstly get contact with the substrate, so actually there will be more. Excuse me. Oh, sorry. Yeah. So, so actually, when it comes to dynamic wetting, if we put a droplet on a substrate, if we observe all the dynamic process, so actually there will be more mechanisms that come into effect. So, so if we consider the most simple case, for example, if we put a non-volatile Newton fluid, for example, low viscosity silicon oil on a solid substrate. So actually, this phenomena is controlled by the computation between the capillary forces and the viscous dissipation. So actually, if we so actually the computation between the capillary forces and the viscous dissipation will give rise to the classical Tanner's law, which is proposed by Professor Tanner in the late 70s. So if the liquid become volatile, either from silicon oil, for example, when the liquid become volatile, so actually there will be more effect that come into play. So actually, because of the evaporation effect, that is because of the preferential evaporation, especially near the contact line. So we can see that even a droplet that is initially calculated as complete wetting based on the based on the Young's equation, so it can actually sometimes exhibit a pseudo-stable droplet shape with finite contact angle. So actually, this is pointed out in these different publications, so the thing is, what else? Is there any other mechanisms that would come into play besides the capillary effect, viscous dissipation, and the evaporation effect? So, yes, the answer is yes. In the past several years, there have been several publications which point out that besides the capillary effect and the viscous dissipation, and besides the evaporation effect, there will be also the thermal Malongoni stress that will potentially play a role in the dynamic wetting or in the droplet shape. So the thing is that how does this capillary effect, viscous dissipation, evaporation, and thermal effect actually interact with each other? So with this goal, the first thing we do is that we establish a numerical model. And this is one model basically on a single component droplet. And especially we consider the boundary equation and the liquid gas interface, the governing equation, especially at the liquid phase, as well as the heat transfer across the solid substrate. So this model is actually based on the lubrication theory, in which assumption we assume that the droplet is a very thin droplet. So with this assumption, we can simplify the momentum equation so to better solve the system of the problem. So, and also across the solid substrate, we consider one-dimensional thermal transport process. And also we derive the expression of the interfacial mass flux based on the Hertz-Knudsen equation. So this is a summary between what we considered about the governing equations in the liquid phase, as well as the boundary equations and the liquid gas interface. So, and we additionally did some more simplifications based on these equations, and we also applied some approximations, and this system is actually solved by the finite element method. So I will not explain more details about the derivation of these mathematical equations, but finally, we can arrive at 5 equations along with 5 independent variables, so that actually this system of the governing equations can be solved. And this is the boundary equations and the initial equations we applied to this system. And here is what we got. And this is a demonstration of how the flow field develops during a droplet evaporation. So we can see that at the very initial stage, when a droplet gets contact with the solid substrate, you can see that there is an outwarding capillary flow. So at the very initial stage, it's capillary dominated. And then because of evaporation effect, because of the formation of the temperature difference and the droplet surface. So you can see that a thermal-Malangoni flow will develop, and which will reverse the flow direction inside the droplet, and it will form a vortex inside the droplet until the droplet fully evaporates. So this is how the flow field developed when a droplet contacts the substrate and when it evaporates. So, and this is the decomposition of all the different stages when a droplet evaporates. So here we developed it into the capillary stage when a droplet initially gets contact with the substrate, so which is dominated by the outwarding capillary flow. And then the second stage with the Hansen-Malangoni flow, which actually the flow strength become bigger and bigger, and it finally form a vortex inside the droplet and until the droplet fully evaporates. So what we will focus on here, so one point is that we care about the formation of the stagnation point near the contact line. So actually when we do see the numerical result, we can see that there is a stagnation point and forms at the base and near of the droplets near the three-phase contact line. So the question is that does this stagnation point that forms near the droplet contact line universally exist? Yet another question is that actually in this paper by Sarah's group, actually they point out that the thermal Malangoni flow can have some influence on the shape of single component volatile droplet on thin and completely wetting substrate. So the question is that does the thermal Malangoni flow always play a role in different kind of liquid and on different kind of substrate? So this is a question. So what we would like to answer is that when does the thermal Malangoni flow is significant and when is it negligible? So with this goal, we actually did a lot of numerical simulation with different combinations of liquid and solid. So actually this figure, you can see that this y-axis present the substrate conductivity. You can consider it as a substrate conductivity. And this is foam glass, which have low substrate conductivity. And here is copper, which have high substrate conductivity. And also in the x-axis, in this axis, it actually represents the liquid volatility from the right to the left. The liquid volatility is increasing. So if we compare this column, we can see that actually with increasing substrate conductivity, you can see that the temperature gradient and the droplet surface is becoming larger. And also, if we look at this column, so we can see that with increasing liquid volatility, so you can see that the interfacial temperature temperature difference is the largest when the liquid volatility is moderate, while when the liquid volatility is very high, for example, when the droplet is very much volatile, you can consider that in this case, the droplet surface is uniformly cold. So in this case, the temperature gradient is small. And also, if the liquid volatility is very low, that is, if the droplet nearly evaporate, in this case, it's kind of like isothermal state. So in this case, the temperature difference and the droplet surface is also very small. So, and we all additionally decomposed the interfacial volatility based on our mathematical formulation. So correspond with our simulation result of the temperature field, we can actually see that correspond with the temperature difference and the droplet surface. You can see that actually the thermal Malangoni flow, which is presented by this red dot line, becomes the largest when the substrate conductivity is high and when the liquid volatility is moderately high. So at this position. So and this is a summary of all the flow state and the temperature field in different scenarios with different liquid volatility as well as with different substrate conductivity. So we can see that actually at this state, the temperature field is very much apparent, and because of the large temperature difference and the droplet surface, so actually in this case, the thermal-Malangoni flow is the strongest, which actually reverses the flow field inside the droplet compared with these isothermal cases. So to give a summary of the dominating mechanisms, so actually based on our mathematical model, we can see that the flow field inside the droplet can be explained by three dimensionless numbers. One is the Jacob number, which can be regarded as the strength of the interfacial thermal effect, that is how much heat is taken away from the droplet surface. And the other dimensional number is the Belt number, which present the ability of heat dissipation into the substrate. And actually, the Jacob number and the Belt number decide the temperature field inside the droplet, so which will form a temperature gradient across the droplet. And actually, this temperature gradient will decide and the Malangoni number, which is a relative strength between the Malangoni effect and viscosity effect, and based on the Malangoni number, it will decide how strong the Malangoni flow is. That is, if the viscosity effect is small, if the liquid viscosity is small, then the Malangoni flow will be stronger. So actually, the temperature field along with the liquid viscosity actually decide the strength of the Malangoni flow here. So, and again, the Malangoni flow in competition with the capillary flow will decide the flow state inside the droplet. So, and additionally, based on this dominating mechanism, we actually form a phase diagram based on our analysis before. So this axis is the Jacob number, and this axis is the Belt number. So Jacob number can be regarded as the expression of the liquid volatility, and the Belt number can be regarded as the ability of heat dissipation into the substrate. For example, with changing substrate conductivity or with changing substrate thickness. So with this, we actually divided one region with flow reversal and droplet surface. So actually, and then we can divide this phase diagram into three regions. So actually, in the first region, which in this region you can regard that the droplet is near is rarely evaporate. The volatility is very small. So in this case, actually it is close to our isothermal state. So in this case, it is the capillary effect that dominate the droplet dynamics. So as the liquid volatility increases, then it comes to region 2, and actually in region 2, because of the evaporation cooling effect and because of the enhancing thermal Malangoni flow, so actually the thermal Malangoni flow will reverse the flow direction, especially near the contact line, and it will form a stagnation point near the contact line, and then it will come with a flow reversal and droplet surface. And then if we further increase the liquid volatility, when the droplet become highly volatile, for example, in a flash evaporation case, or evaporation of a refrigerant on a heated substrate, then the strong evaporation flux and the contact line will become dominant. So actually, this preferential evaporation near the contact line, this strong evaporation mass flux will actually retard the spreading of the droplet. And so for the slow state of the within the droplet, we actually did some more comparison with previous publications. So actually, we compared with these two papers from Stone's group and from Law's group. So actually, our prediction of the regime with flow reversal and droplet surface actually correspond with their experimental result with different combinations of droplet and substrate. And also, actually, this numerical result also correspond with the result of Li et al. So actually, in their results, they increase the volatility of the droplet by heating the substrate. So by heating the droplet, by heating the substrate, actually increases the volatility of the liquid, increases the saturation vapor pressure. So in this case, the thermal Malangoni flow also becomes stronger. And so in their research, they actually observed a transition from the coffee run to the coffee eye. So, and additionally, we investigated the spreading dynamics of the droplet based on another derived phase diagram, which is also based on the Jacob number and the Belt number. So we can see that with increasing liquid volatility and always increasing substrate conductivity, actually the droplet, the spreading rate of the droplet becomes smaller and smaller, and it changes gradually from the region that is dominated by the Tanner's law, which is 1/10. It changes gradually, the spreading rate decreases gradually to a smaller value. So, and then we checked the flow state and the different point of this phase diagram. So we can see that when the liquid volatility is very small, or when the substrate conductivity is very low. So actually, in this case, the droplet spreading is dominated by the capillary effect. So in this case, the droplet the spreading rate follows is close to the Tanner's law. And then if we further increase the liquid volatility or the substrate conductivity becomes stronger, and then you can see that the thermal Malangoni effect becomes stronger, and then the evaporation mass flux also becomes stronger, especially near the three-phase contact line. And if we further increase the liquid volatility and further increase the substrate conductivity, we can see that actually in this case, the preferential evaporation near the contact line become very strong. And also, along with the evaporation cooling effect, the thermal Malangoni effect also, flow also become very strong, which actually reverses the direction of the flow and the droplet surface. So this is the phase diagram for the spreading law. And additionally, we did some experimental verifications on this numerical result of the spreading rate. So we actually tested 3 different type of substrate, which is copper, sustained steel, and glass. So we each have one order of magnitude higher thermal conductivity. So by testing all these different type of substrate, we actually see, for example, from 3 to 4 to 5. This is glass, sustained steel, and copper. So we actually can see we actually can see a decrease in the spreading rate. And also for 6, 7, 8, so we can also observe that as the thermal conductivity of the substrate increases, actually the spreading rate decreases. And additionally, we did yes, and besides our experimental results, so actually our this prediction also correspond with this series work, which actually did some more experiments with decreasing glass thickness. So actually, by decreasing the thickness of the glass substrate, they are actually correspond to a decreasing Belt number, which can be explained in this phase diagram. So actually, in this work, they also observe a slowdown of the spreading with decreasing substrate thickness, which actually correspond with our prediction based on this phase diagram. And this is the substrate conductivity. And we additionally did some more experiments with different type of liquid, including butanol, IPA, and FB72. So These three different type of liquid actually each have one order of magnitude higher saturation vapor pressure. So with this different type of liquid, we are able to evaluate the influence of the liquid volatility. And this is our experimental data actually from 2 to 5 to 8. So it corresponds to butanol, IPA, and FC72. So we can see a readily decreasing spreading rate of the liquid droplet. And additionally, if we further heat the substrate, for example, from 8 to 9 to 10 to 11, with substrate heating, we can additionally see a further decrease in the spreading rate of the droplet. And actually, beside the spreading rate of the droplet, we can also observe a decrease in the spreading period of the droplet. So, and actually, if the liquid volatility become very high, actually we can the spreading period become indistinguishable. So that we cannot recognize where the spreading period is if the liquid volatility of the droplet become very high, if we further increase the substrate temperature. And actually actually I think that this if we further increase the substrate temperature, it actually approach the boiling point of the droplet, so that no spreading will be observed anymore. So this actually corresponds to the flash evaporation condition. Actually, that is like if you put a droplet of refrigerant on very hot substrate, so actually it will evaporate immediately, so you cannot observe the spreading of the droplet anymore. So that is a simple explanation of this trend of the spreading the spreading rate. Yeah. So this is some experimental result. And also, yes, or this is another work by Kuma et al. Who presented last year in APS-DFD. So actually, they use different type of liquid. So I noticed that actually they got the same conclusion that is predicted by this phase diagram. Okay, and this is a summary between all the experiments we have done, and along with the numerical prediction of the spreading rate. So we can see quantitative correspondence between our experimental result and this numerical simulation on all the cases on different type of liquid and on different type of solid substrate. So yeah, so which verified the validity of this phase diagram on predicting the spreading dynamics of a specific combination of liquid and solid. Yeah, so to give a summary of the wetting dynamics of single component droplet. So actually here, by combining numerical simulation and experiments, we actually find that the wetting dynamics of volatile droplets can be scaled by the spatial temporal interplay between capillary effect, evaporation effect, and thermal-Malangoni effect. So, and we also proposed a unified criterion for the flow reversal and the formation of the deposition pattern and different combinations of liquid and solid. And also, we found that the spreading law can changes from the Tanner's region, which is 1/10, gradually to a gradually decreasing value along with the increasing of the saturation vapor pressure of the liquid from 10 to 10/4 Pascal, and also with increasing thermal conductivity from 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ this is a brief summary of the single component droplet. So, and actually this work is currently in revision in GFM. So actually this work has some further implications for practical application. The first one is that actually this work establishes a framework for predicting the wetting behavior of the volatile droplet on different type of substrate, so that we in actual so that we can predict the wetting behavior with different combinations of liquid and substrate. And additionally, it can also instruct us to rational design, rational choose the solvent and the substrate condition for uniform coating. For example, in the formation of perovskite solar cell 2D crystals, or in the inkjet printing LED. So we could choose the solvent type or the substrate type correspondingly, so that it can form a more uniform deposition for better energy efficiency. So this is some implications for practical application. So actually, so as I mentioned that, so for a single droplet, we can see that the wetting dynamics is dominated in our with our numerical result. It is dominated by the capillary effect, evaporation effect, and the Malongoni effect. So actually, this is highly related with the flow structure near the three-phase contact line. And actually, about more details about the flow structure near the three-phase contact line is also one issue that is proposed by one of our reviewer in GFM. So we actually did some more thinking or did some more explorations on the flow structure near the three-phase contact line. So actually, for the flow structure near three-phase contact line, it does not only play an important role in the evaporation of droplet. It is also highly related with, for example, in boiling. Actually, in boiling, there will always form like ultraflux thin film. So actually, in this case, this flow structure near this three-phase contact line also matters the efficiency of the boiling heat transfer. And also, for avoiding or for utilizing the coffee rain effect, it is also highly related with the structure with the flow near the three-phase contact line. So actually, as I mentioned before, that based on our mathematical derivations and analysis, we actually concluded three-dimensional numbers that governs the flow field inside the droplet, which is Jacobi number decided by the liquid volatility, the Belt number decided by the substrate conductivity, and also the Malongoni number, which present the relevance between the which measures the relative strength between the thermal Malongoni effect and between the Malongoni effect and the viscous effect, so these are two additional demonstrations of one low volatility case and one high volatility case. So again, that we can see that for low volatility case, the flow field inside the droplet is actually dominated by the capillary flow. So the flow field is roughly the flow field is like all the way outwarding towards the contact line. While when the droplet become volatile and the substrate conductivity become larger, we can see that because of the evaporation cooling effect, the thermal Malongoni effect becomes stronger and it will form a stagnation point near the droplet surface. So it actually did some more further investigation onto the details of the flow structure near the three-phase contact line. So, and this is some enlarged result of how the flow field is like near the three-phase contact line. So so again, the question is that what actually causes the formation of the stagnation point and the reversal of the interfacial flow. So actually, here are two classical work, one by Professor Luo's group and one by Professor Stone's group. So actually, in their research, they actually point out that the change of the temperature gradient across the droplet surface causes the reversal of the interfacial flow, and also causes the formation of the stagnation point near the three-phase contact line. Yeah. So actually, in the reason in their work is that it is attributed to the non-uniform distribution of the interfacial mass flux. As we know that the interfacial mass flux is very much strong near the contact line than in other area. So the non-uniform distribution of the interfacial mass flux and also the ability of heat dissipation into the substrate, these two mechanisms actually lead to the change of the temperature gradient near the contact line area. However, as I mentioned before, that in our numerical simulation, we actually did not see a did not see a did not see did not see a gradient, or we did not see a change of the temperature gradient and the droplet surface. So actually, in our numerical result, we actually see that the droplet become colder near the apex area, and the droplet and the surface temperature is apparently higher near the droplet edge, and and this is some more summary of our simulation result. So we can see that in our based on our numerical result, we can see that for different type of liquid and for different type of substrate, we can see that the droplet apex is kind of is cold, and the area near the contact line is warmer due to the efficient heat supply from the solid substrate. So the question is that, so what causes the discrepancy between our numerical result and this numerical result, which indicates the change of temperature gradient and the contact line area? So actually, we checked the derivation in these different works. So actually, their derivation is based on the expression of the interfacial mass flux, which is derived through the electrostatic analogy. And and additionally, actually, this electrostatic analogy is based on an isothermal assumption. That is that they did not consider evaporation cooling effect. So basically, they actually overpredict the evaporation mass flux near the three-phase contact line. So actually later in this work by Professor Wilson, they did some more modifications with the expression of with the expression of with the expression of the interfacial mass flux. So actually they applied the evaporation cooling effect on the expression of the interfacial mass flux. That is that they consider the effect of evaporation cooling on the reduction of vapor pressure. So with this modification, they got this temperature profile, the temperature field, based on their result, both numerically and experimentally. So actually, you can see that their result correspond with our result, which shows a monotonic distribution of the temperature, which have a cold droplet apex and also a warmer edge near the contact line area. So actually, in our result, the interfacial mass flux is derived based on the Hertz-Knudsen equation, the chemical potential equilibrium, and the liquid gas interface, and based on our ideal gas assumption. So this assumption actually also considers the curvature effect and the droplet surface, as well as the influence of the temperature difference, as well as the vapor concentration difference. So, and additionally, actually our result, as well as Professor Wilson's result on the temperature field correspond with experiments by infrared camera. So this is only one example I got from the literature. So there have a lot of other publications which also indicate that actually the temperature field and the droplet surface is monotonic, so which have a cold apex and also a warmer edge near the contact line area. So this is further discussion of the flow structure near the three-phase contact line. So yeah, So the thing is that yeah, and then it comes to the original question that if the temperature distribution is monotonic, if there is no change in the temperature gradient, then what causes the formation of the stagnation point? So, and additionally, so we take further look at the decomposition of the surface velocity with our mathematical derivations. So here is the expression of the surface velocity in our model, and we divided it into the capillary velocity and the thermal Malongoni velocity. If we further look at the expression of the P here, the liquid pressure here, so we can see that actually this Laplace pressure, this pressure is originated from the interfacial tension and the surface curvature, so which actually will form yes, yes, and actually, this is if we take further look at this expression of this pressure here, so it can be actually it is mainly contributed to the attributed to the surface tension as well as the droplet shape or the droplet curvature, the curvature of the liquid gas interface, as well as when some influence from the van der Waals force or the gravity term, which can actually ignored because they become very small when the droplets when the liquid film thickness become it is when there is a finite liquid film thickness. Yes, so actually these two terms can be neglected. So what dominate is the surface tension and the curvature of the liquid gas interface. And additionally, the thermal Malongoni velocity is originated from the temperature gradient due to the evaporation cooling effect. So actually for non-volatile droplet or for low volatility droplet, so actually the flow field is dominated by this capillary effect, which is originate from the surface tension and the droplet curvature. And if the droplet become volatile, so there will be a strong evaporation cooling effect. So in this case, this thermal Malongoni velocity, which originates from the temperature gradient, become large. So it actually reverses the flow direction near the contact line and will form a stagnation point near the droplet base, near the contact line area. So this is a further discussion of the flow structure near the contact line. And we did further visualization with micro-PIV. So what we choose is the butanol liquid and the IPA, so which have different saturation vapor pressure, and this is some result of the micro-PIV. So actually for low volatility butanol, we observe a outwarding capillary flow towards the contact line, while for more volatile IPA droplet, we actually observe a reversal of the flow field near the contact line area. So, and also this also corresponds with the final deposition pattern we got. That is for low volatility solvent such as butanol, there is kind of like a coffee rain effect. And when the solvent volatility become high, so you can see that because of the flow reversal and the droplet surface, it actually the deposition pattern become more focused in the inner region, which causes the transition from a coffee rain effect to a more interior deposition. So, okay, so to give a summary of this part, so actually here we further checked more details about the droplet about the flow structure near the contact line, and we concluded that actually it is a joint result of the capillary flow and the thermal Malongoni flow, and the previous theory in some publications on the non-monotonic temperature gradient. It is resulted from the over prediction of mass flux near the contact line because they utilized the isothermal assumption, so they did not consider the evaporation cooling effect. So and yeah, And in our with our micro PIV check, with increase in liquid volatility, we can see that the thermal flow got stronger, and it causes the transition from the coffee run to a more interior deposition patterns. Yeah. So yes. So actually, for some more applications, if we focus on the flow structure near the contact line, we can see that the capillary flow actually drives the liquid to wet the solid surface. So actually, in boiling or in evaporation, to avoid dry out, we should enhance the capillary flow by adding some porous structure, etc., some wicks, etc. And also with our further experimental result, we can see that by using a single solvent, it's actually the ability in the control of the deposition pattern is quite limited. So this actually calls for the introduction of the soluto-malongonic flow by involving binary or ternary solvents, which have already been utilized in the fabrication of 2D crystals or the quantum dot LED. So yeah, so this actually calls for more exploration of the mechanisms from single component droplet to multi-component droplet. So as I showed here, so multi-component droplet actually is the most common existence in nature. So we are drinking wines, we are using fuels, we are also using inks, and also in the industrial field, we are also using different kind of inks to form LED, etc. And also the seawater is also a multi-component liquid. So what I talk here is about the saline solution droplet, which is only one representative of multi-component droplet. So actually the governing mechanisms can be further extended to other type of multi-component droplet. And this is some background of the a special type of salt I investigated. So which is such as lithium bromide or lithium chloride. So when we mix them with water, we can got a hygroscopic solution, which can actually absorb water vapor because of the reduction of the vapor pressure and the droplet surface. So compared with evaporation, it will have some, in high humidity, it will have opposite mass flux, and it will have advancing contact line. And different from evaporation cooling, it has some absorptive heating effect, and also it will have some solute effect within the droplet because of the existence of the salt ions. Yeah. So and additionally, yeah, with this is the mathematical model, and based on and different from the single component model, here we also consider the concentration equation in this governing equation in the liquid phase. And on the liquid gas interface, we consider the concentration balance. So, yes, the interfacial mass flux is again derived based on the Hertz-Lorentz equation and the chemical potential balance. Yeah, and here are some numerical results about what happens inside this hygroscopic saline solution droplet. So here, actually, we can see that in this case, besides the capillary effect, besides the thermal-Malongonic effect, actually the soluto-Malongonic effect also start to play an important role. So, and actually, the droplet dynamics, the prediction result of the droplet dynamics actually depends on the coefficient setting in our expression of the interfacial mass flux. So in this case, that yes, you can see that by changing this coefficient, we can actually see the different interaction between the soluto-Malongonic effect and the thermal-Malongonic effect. So, and then we can see that the droplet spreading which is governed actually by the competition between the capillary, soluto, and the thermal-Malongonic effect. So and again on this sealing on the spreading dynamics of this sealing solution droplet, we also did some more experimental verifications, and especially as I mentioned that we are using a lubrication type model, so we need to treat the substrate with some plasma treatment, so make it super hydrophilic. So and then we did some spreading test on the droplet. And we actually, based on the experimental result for this special type of sealing solution droplet, we actually divide the spreading stage into 3 stages. The first stage, it is dominated by the by the combined result, by the combination between the capillary effect and the Malengoni effect. And the stage 2, the Saluto-Malengoni effect and the thermo-Malengoni effect become very much apparent. So their competition actually decide the spreading rate of the droplet. And the stage 3, the droplet gradually reaches equilibrium with the ambient. And here are some more simulation, a comparison between our simulation result and the numerical result. As I mentioned that actually the coefficient setting in the numerical model is very important. So actually by modifying the coefficient setting, so we can actually explain the droplet dynamics observed in our experiments. So here is some more brief summary on this work on this hygroscopic sealing solution droplet. So actually we can see that different from the mechanisms in the case of single component droplet, in the case of sealing solution droplet, the Saluto-Malengoni effect start to play a role. So in this case, the relative strength of the capillary thermo-Malengoni and Saluto-Malengoni effect, it changes along with time and water and phase change happens. And actually, this different effect decide the spreading behavior of the droplet. And then we did some more experimental verification, and we explained these experimental observations based on our numerical result on the by exploring the governing mechanisms. Okay, so actually, as I mentioned that there in nature, there are all kinds of multi-component droplets. Actually, besides sealing solution droplets, there are also a lot of many other type of multi-component droplets, such as binary mixture or droplet with surfactant, etc. So so here is a review of the governing mechanisms in a multi-component droplet. So actually for multi-component droplet, usually we can say that there will be difference in the component volatility. So actually this difference in the volatility of different component will causes the preferential evaporation or the concentration evaporation near the Tangleland region. So actually, for example, in this work, so actually they can observe this phase separation inside the droplet due to preferential evaporation of highly volatile solvent. And also the evaporation effect or the non-uniform distribution of the interfacial mass flux will induce the temperature gradient, and the temperature gradient, as I mentioned before, along with the evaporation effect, will influence the wetting dynamics of a single component droplet on a substrate. And additionally, the thermal if the liquid volatility become very high, so actually this temperature gradient will form a hydrothermal wave and the liquid gas surface. So which is also observed by infrared camera by very relevant groups. And also additionally, beside the temperature gradient, this preferential evaporation of highly volatile solvent will also cause the density gradient, so which will also sometimes will induce a Rayleigh Taylor instability, which also reported here in this work. And additionally, the preferential evaporation, especially in the Tangleland area, will also cause this concentration gradient. And also the concentration gradient and the temperature gradient will together causes the surface tension gradient, and the surface tension gradient, will correspondingly, induce the saluto-Malangoni flow or the thermo-Malangoni flow. So, and the further utilization of the thermo-Malangoni effect. So actually there are some applications of the self-rewetting fluid in heat pipe, so that by utilize this thermo-Malangoni effect, so we can avoid some, to some degree, to avoid the dry out in heat pipe, etc. And and also if the droplet is no longer is no longer a capital type, if the droplet is is elongated, or if the droplet is a triangle type, etc., it actually can drive some more beautiful additionally flows inside the droplet, which is also due to the thermo-Malangoni effect induced by the non-uniform temperature distribution and inside the droplet. And also, again, the saluto-Malangoni effect as revealed in our research, as also as in Diden's work in this work. So actually, the saluto-Malangoni effect will also causes the spreading or contracting effect, both for for multi-component droplet, for example, saline solution, or in a binary mixture such as alcohol and water. So actually the saluto-Malangoni effect in the case of multi-component droplet become more apparent than the thermo-Malangoni effect. So this is one mechanism we need to potentially we need to specially take account of when we consider a multi-component droplet. And one additional phenomena is the density gradient will also cause Rayleigh convection. So when the Rayleigh flow dominance in specific combinations of liquid mixtures, you can see that actually in some cases the gravity effect will become stronger than the saluto-Malangoni effect. So in some specific cases, actually the gravity effect will dominate the flow structure, the flow pattern inside the droplet. And also in some other cases, the Rayleigh convection and the saluto-Malangoni effect, they might compete with each other. So depend on their relative strength, they will cause even more interesting or more colorful flow patterns inside the droplet.
Dr. Wang,
yeah.
Yes, maybe
Yes.
to give some space and time to questions, if you could conclude.
Yeah, this is the final. Yes.
Oh, perfect. Oh, perfect.
Yes.
Okay, thank you.
So this is a review of all the governing mechanisms. So if you are interested, you are welcome to look more into these two review paper, which is published in previous years. And yes, and this is So and finally, this is our group and Kyushu University, and you are most welcome to visit us. So we have a big group of thermal science. We are doing different field related with phase-stage heat transfer or heat conduction and different scales. So yeah, you are most welcome to visit us. Visit Fukuoka. It is a very beautiful space. So, and last, I'd like to thank my collaborators in Kyushu University, University of Edinburgh, Aristotle University, and Tsinghua University. Yeah, thank you. Thank you very much.
Thank you. Thank you very much, Dr. Wang, for the very interesting topic covering different research studies. So I'm sure there will be questions. So I open now the stage to question. Otherwise, yes, Professor Bucci, maybe.
Yeah, I have a first of all, it's an excellent work, and I really enjoyed it until the end. I have a couple of questions. So, for sake of time, you never mention specific heat and density of the substrate, or at least I didn't catch exactly where. But my intuition will suggest that the substrate effusivity, so rho KCP, is very important, not just the conductivity and the thickness. And maybe I missed this detail in your slides, but I wonder whether you have tested the effect of K, other than the effect of K, also the effect on rho CP, if not, for a real material, at least for a, theoretical material.
Yeah. Yes. Thank you very much. I think what you mentioned is a very important point. So actually for rho CP, I think that is especially become very important if the time period become very small. So if it is a transient heat transfer case, for example, in spray cooling, actually the rho CP is the thermal diffusivity become very important. So actually, in our case, it is evaporation or droplet spreading or droplet. So actually, in this case, the time scale is in second scale. So I think it is kind of different with spray cooling. Spray cooling, it can be like a millisecond scale. So in that case, I think the rho CP, the thermal diffusivity, become very important. But in our case, the time scale is larger. So I think still can explain.
Thank you.
Thank you.
This was a question. I'm also interested to ask you regarding the let's say you showed that the Marangoni effect becomes large and create and form the stagnation point. I wonder if there are conditions after which, in a way, the Marangoni effect doesn't have an impact anymore. For example, when the heat flux of the substrate of the solid surface is very high, or for very high temperature application, would you still expect the Marangoni effect to play such an important role, or no?
Yeah, I think, as I mentioned before, I think the role of the thermal Marangoni effect, it actually depends on the condition of the substrate. Yeah. And also it depends on the volatility of the liquid. So it depends on the combination. It depends on what kind of liquid and what kind of substrate you are using. So yeah, in specific regions, such as in this region, when the liquid in the substrate conductivity is high, and when the liquid volatility is moderately high, actually in this case the temperature gradient and the droplet surface is the highest, and in this case the thermal Marangoni effect is strong enough to reverse the flow direction. While in other cases, for example, in this case it is close to isothermal case. So in this case, because the droplet volatility is very low, actually in this case, the evaporation cooling effect can be neglected. So in this case, it is capillary dominated. And in region 3, in this case, the droplet become highly volatile. You can imagine that if a refrigerant is dipped on your hand, it kind of, the droplet surface become uniformly cold. It become very cold. In this case, the temperature gradient is also small. So in this case, the thermal Marangoni flow is also weak. Yeah. So it depends. It depends on the combination between of liquid and solid.
Clear. Thank you very much for your reply. Let's see if there are other questions from the audience. You can even drop your questions in the chat.
Oh, I can see a question
yes.
from Otif. Yeah.
Yes.
The effect of liquid volatility. Estimate the timescale onset. Okay. The onset of thermal and solidal flow and how it would affect the transient associated. Oh yeah, I see. So actually the time scale, from my point of view, I think the time scale can be very small. So actually, actually for the, the capillary dominated stage, only happens very quickly when you put a droplet. When the droplet when you put the droplet on a substrate, it is capillary dominated. So actually it spread very fast. In this case, it is capillary dominated. So, but as long as the liquid volatility is high, evaporation will happen. So as long as the evaporation happens, there will be temperature gradient. And if there is temperature gradient, there will be thermal Malangoni effect that come into flow, that come into play. So yeah, so I think it also, the time scale also depend on the volatility of the liquid. If the volatility of the liquid is small, in that case, the capillary dominated region will be, will be longer, or it will be capillary dominated. But as the liquid volatility becomes strong, so I think due to the very quick evaporation cooling effect, if the liquid is very volatile, in this case, I think the temperature gradient will establish very quickly, and the thermal Malangoni flow will also develops very quickly. So it depends. Again, it depends on the volatility of the liquid. So this is my point of view. I hope it can answer your question, Atif.